As fossil fuels continue to diminish and become more expensive, solar energy is quickly emerging as one of the largest and most accessible sources of energy. New technologies will continue to emerge as solar energy is invested in more, but some main issues of solar energy need to be addressed. Those main issues are balancing land use with energy production and aligning peak energy demand with the availability of sunlight to supplement that energy usage. Therefore, we were contracted to develop a hydroelectric storage system that would use solar energy to pump water into a reservoir and then could use that water when supplemental energy was needed to create electrical energy by running it through a turbine. Our job was to design a hydroelectric power plant with the highest efficiency possible while costing the least amount of money.
In order to create a successful energy storage system, the system needed to be as efficient as possible in multiple aspects while being the cheapest to build and possibly repair and maintain. In addition, the storage system should do as little environmental and societal or cultural damage as possible. It should not offend or affect the people in the area, should be safe and around people, animals, and plants, and should have the overall least effect on animals and plants. Lastly, the system needed to be able to output 120 megawatt hours of energy in under 12 hours. While solar panels may be able to directly source energy during daylight, extra energy or energy during a time without sun is still needed. We made a Gantt chart, a needs finding table, and other planning figures to help us along the way.
Our modeling approach consisted of identifying relevant factors that would affect our energy input and then finding equations that we could use to find values for those losses. We created a system representation diagram as shown that had our losses, which were pump and turbine efficiency losses, friction losses from the pipes going both up and down, and energy losses due to the turbulent flow at the bends in the pipes. We also considered accounting for reservoir leakage, energy loss to damaged equipment, and volume loss due to leaks in pipes. The reservoir leakage was the closest to being included in the model, since leakage is based upon the permeability coefficient of the reservoir and its surface area. Because we used the largest surface area possible of all those sites, the leakage seemed considerable at 3.6 meter cube per second, which ended up around 300,000 meter cube per day. However, this was using a high coefficient of permeability, and when we researched what our reservoir would be made of and how compacted the soil would be, while still using a conservative number, it only resulted in about 15,500 meter cubes per day, which was less than a percent of our overall water volume. Thus, it did not need to be considered. The energy losses due to damaged equipment also seemed significant at first. According to a study done by the Laboratory of Hydraulics, Hydrology, and Glaciology at the Swiss Federal Institute of Technology, hydroabrasive wear, which is the wearing down of equipment due to sedimentation, can account for about 0.9% of a loss in efficiency in a 6-month period. However, they later concluded that those losses could be prevented by doing routine maintenance work, and after researching the cost of maintenance, it would be about $10,000 every year, which would not be enough to be factored into the model. Finally, the leak rate is based upon the discharge coefficient, the crack area, the pressure drop, the specific gravity of water, and mass density of water at standard conditions. And when we computed all of those, the loss per day was only about 56 meter cubed, which is rather insignificant when compared to how many our volume we'd be pumping through the pipes each day. So overall, our modeling approach was based upon factors that significantly impacted the efficiency or the cost of the plant.
The method we used was Python code that ran through every possible combination of part parameters in order to find the optimal configuration. The main function iterates through each parameter using nested for loops and then passes those parameters along with some inputted and calculated values to a function. This function contains our model, and using the passed parameters, it calculates two things: the energy in and a configuration score. The energy in is calculated using the model, and the configuration score is a score weighted using the Cotter's method sensitivities of the different part costs.
The model for our code went through several iterations. At first, the code we wrote optimized for efficiency, disregarding price. We thought that spending more money in the short term would help us gain more money from the system in the future. While this is true, the time for us to turn a profit from the money we spent in the short term was deemed too long of a time by the group. We ended up optimizing our value at 0.75, but the price was far higher than what was anticipated. To change this, we decided to weight all the scores by price using Cotter's method. This implementation works successfully and optimizes equipment used at the lowest price. Also, even though our reservoir would be able to supply 17.5 megawatt hours, which is our peak energy demand, for a full 12-hour period, we decided our system should be optimized to provide 10 megawatt hours for 12 hours, which would be our average energy demand. As a result, the system will be optimized for the most common usage state, but will still be able to provide peak energy demand in an unoptimized state. We concluded that the optimal energy of our system would not be used at any high frequency, so our model was changed to create the best usage of the options provided instead.
As seen by the tables, the code had multiple inputs and outputs. Because we used Cotter's method sensitivity values, we were able to determine what aspects of the system were most and least important. From our Cotter's method, we found that the turbine efficiency was the least important aspect, so we did not spend as much on it. Also, the efficiency of the entire system is 70%, placing it right in between older systems of about 60% efficiency and state-of-the-art modern systems of about 80% efficiency. In order to get 120 megawatt hours of energy, we needed to input 170 megawatt hours of energy. The reservoir would take 8 hours to fill and 12 hours to empty. Lastly, the entire cost to prepare and build the system is just over $660,000, making it very affordable in relation to other systems like it. The additional money saved can be used for quality maintenance and repair if needed. As seen in the picture in the top right, we chose Site 1. It had the least preparation cost, cultural and societal concerns, and the environmental impact was limited. Site 2 was a sensitive area to the Native American population and had the potential for a lawsuit or other devastating problems. Up front, Site 2 would cost at least $60,000 more than Site 1. Site 3 had many environmental concerns about erosion that may have a larger effect in the future. Up front, Site 3 would cost at least $80,000 more than Site 1. Money saved from the building of the system may have to be used to decontaminate the water in order to diminish the negative effects it might have on the wildlife in the area.
Looking at the main program, first the code prompts the user to input their desired efficiency, between 0 and 0.75 exclusive. Next it defines several variables. Each parameter from the parts catalog has a list of values that will be iterated through in the body of this program. Below the parameter value list are the calculated and known values. Some of these are known constants like energy out, and some are values calculated earlier, such as the mass and volume of water and the length of piping. At the bottom of the calculated variable section is where the user inputted target efficiency is converted into a usable target energy input. The body of the main function uses nested for loops and runs through each value in the parameter value list shown earlier. Within the for loop, there is a quick calculation for upwards and downwards velocity that uses the current value of the pipe inner diameter and the previously calculated values for pump and turbine flow rates. The centerpiece of the main program is when it passes the needed values to the model function code, which we will go into later. The model function passes back an energy input and a configuration score for each configuration of parameters. The conditional statement below the function call selects the configuration with the best configuration score that matches the target energy and efficiency. If the conditional registers as true, the current configuration is stored to be printed at the end of all the iterations.
The pipe loss coefficient and the amount of bends in the pipes in total. Then, the individual energy losses are individually stored in variable form. The significant losses of energy in the system were the energy loss in the pump, the pipe friction while the water was running up and down, the energy loss in the bends of the pipe going up and down. One of the two purposes of the function is to return input energy value, which caused some issues because in some of the found formulas, input energy was a variable needed. As an example, for the pipe loss calculation, energy in was used, but the variables were rearranged to match efficiency with the output energy to create a value as seen in the code. All of these separate energy losses were summed along with the output energy of the system to find the energy inputted by the system. Also, this user-defined function solved for and outputted a variable called config score, which Ashish will talk about next.
The config score variable stores the configuration score for each iteration of the function and is what the main function uses to select the optimal parameters. The formula for the config score is a modified version of the formula for energy in. Each loss from each factor is multiplied by value that was obtained from the Cotter's method. By inputting the relevant prices into the Cotter's method code that we had written earlier, we were able to get sensitivities from the prices of each component. Cotter's method is able to give us sensitivity values for each factor, telling us what has the most impact. Because these sensitivities were between 0 and 1 and added up to 1, they were perfect for normalizing the data. An early version of the config score had us looking at the efficiency sensitivities rather than the price sensitivities. Using the price sensitivities essentially gives our model the constraint of price. Our use of config score was an alternative to calculating the price of each configuration directly. Without using a two-dimensional lookup table or getting into complicated nested dictionaries, we were unable to assign each configuration a price. The config score approach is much simpler and still quite effective.
As shown by this visual, we inputted 0.25, 0.5, and 0.75 as the efficiencies we wanted the model to optimize for, and the code outputs the energy input needed to achieve the 120 megawatt hours out that the customer requires. The velocity we need going up the hill, the velocity down the hill, the optimal pump that will achieve that efficiency inputted based upon its price, the optimal turbine efficiency based upon its price, and the optimal Darcy friction factor and pipe diameters based upon their prices. Finally, as you can see, as the input efficiency goes up, the parts become more expensive, which makes sense and is a logical validation of our model. The main problem that we are facing in this project is one that engineers currently face today. That problem was how to store solar energy so that it can be used to power electronics when the power grid needs extra energy. The problem is that there aren't many efficient ways right now to store energy without losing a lot of it in the process. This is a major concern for all nations going forward, as a large issue right now is how we are going to keep making sustainable energy for the future. Designs we even considered were large-scale battery-based systems, vacuum-sealed flywheels, superconducting magnetic energy storages, and even compressed/liquefied air. However, the one we chose to focus on this year was a hydroelectric power reservoir, because the other models had too many risks and costs, along with being too complex. Although it may have seemed rather basic at first, it accomplished very nicely what the other systems did and was also highly efficient. Overall, because our hydroelectric storage system optimized for cost based upon efficiency using Cotter's method outputted sensitivities, delivered an efficient power plant, was relatively inexpensive, and met the requirements of the customer, we are certain it is the best available way to build a hydroelectric power plant.